Okay, now let's get started. Today I only have one screen, so I can't see the chat in real time. So we're gonna take a look at the question at the end. Okay. So today we're gonna talk about how to architect joins for analytical databases to satisfy the needs of analytical agents. All right. So let's get started. So first, we talk about the agenda. First, we're going to talk about the new scenario that we're seeing in the field, right? Instead of human, now it's AI, right, in the query, right? And not surprising, they make every query ad hoc, right? The query that they run today has never been run before, probably never going to be run again in the future. And that creates, problems, right? And also, we're going to talk about the cost of avoiding joins, the cost of having a denormalization pipeline. And then we're going to dive deep into the architecture. We're going to talk about how a query is ran inside of the database, from query planning to data movement, distributed compute, how we scan data, right? All of the things you need, for a fast join, right? And different system miss different pieces of that. So that's why, some of them are slow, right? We're going to talk about those too. And then we're going to give a very brief introduction of PhoenixAI and its join capabilities, related stuff. And then we're going to talk about some success stories from the industry. And then we're going to open for Q&A. Okay, so first, the agentic shift, right? Now, when an agent writes a query, it turns one question into many, many, many queries. Some of them are discovery, right? Some of them are you're just looking at different data, right? And you would want your agents to have access to all of your tables, like to run all of the ad hoc queries on the fly, right? And last year, there's probably a dashboard with like 20 queries that you already know, right? But when the agent writes the queries, everything's ad hoc, right? It doesn't matter, if that table is denormalized, if that query touches how many tables, it does what it wants to do, right? And that creates more pressure on the database layer. A lot of especially real-time data warehouses, real-time OLAP databases, they don't really do joins, right, on the fly, right? Some of them don't even support join. A lot of them don't support horizontally scaling a join, right? But with agentic workload we're seeing today, a precomputation is not going to keep up. It's not just because precomputation itself is very expensive. It's the workload itself just doesn't permit precomputation anymore, right? And the question that the agent wants to ask versus what is already being precomputed, there's a large gap between that, right? Precomputation will still accelerate your queries, right, for your repeated BIs, your reports, but it cannot be something that you start out with, right? Because with your AI analyst agents, a lot of the questions just will not be answered. Okay, so the four requirements that we see, for agentic kind of workload for analytical databases, right? Enjoying is at the heart of everyone, right? You would want to run any multi-table join SQL, a sub-second query latency, right? You would want data freshness to be within seconds. You would want thousands of QPS, even with join queries, and you want everything in one SQL interface. And join is probably we see in the field the biggest bottleneck of them all that we see today. Okay, so let's take a step back and actually look at the workaround itself, right? If your database don't support running joins on the fly, you would rather do a denormalization pipeline, which is a process of turning your snowflake schema, your star schema, multi-table schema tables, and basically do a pre-join and join them into a flat table, right? And this is not even talking about the agentic use case itself. It's a very expensive workaround. I wouldn't even call it a workaround. It doesn't even work for most of the cases, right? Okay, so the first problem is the pipeline you would have to build instead, right? From the source, your multi-table, and going from that to a flat denormalized table, And then to run simple table queries on there, you need a denormalization pipeline, right? And denormalization pipeline by itself, by nature, it is stateful, right? So you need to keep some sort of a state, right? Doing that with a batch pipeline, let's say you don't need good data freshness, right? Just say daily refresh is enough. Using something like Spark is good, right? But if you want real-time data freshness, Spark is not going to keep up, right? You need to introduce stream processing, which is very, very heavy, very error prone, and you need to actually like write code to like maintain it, right? It's very expensive as well. I think the reason, like one of the reason why a lot of the company we see that refuse to go real time is not that they don't need it. A lot of the use that before moving to us, their customer facing use case are not being real time. Some of like that actually depends on the real time component to be their competitor. I think this is like denormalization is one of the biggest blocker with data updates, of course. But denormalization is the biggest blocker for a lot of enterprise going real time because of the denormalization pipeline, because of the stream processing they would have to do with the denormalization pipeline in place. And second is the storage cost, right? A normalized table, it's a reason why normalization has been around for like almost 40 years because it's efficient, right? You would separate different things, right? You will have a fact table and you have some columns that are really repeated, so you take them out as dimension tables, right? So on your most granular table, you don't store every single information multiple times, right? By doing denormalization, you basically flatten it out, right? You're doing the reverse of what we're doing for 40 years. And that, in our experience, 5 to 10x your storage. Most of the is more to the 10x, to be honest, right? And this is not that you're using S3, you're saving your storage by 90%. This is going from 1 time to 10 times. The cost of that is humongous, and also this puts a lot more pressure on your database itself, right? We're going to see a case study of a customer. They used to run almost 50 ClickHouse clusters because of this, because of just the sheer amount of data they have, they need to handle. So they just many clusters to hold these kind of flattened denormalized data. And then after it's denormalized, schema change is going to be way more difficult, right? Let's say you have a fact table here, right? That's like 1 trillion rows. And then you have a dimension table. That's probably like a city ID. You have like 100 rows in there, right? But by creating a denormalization pipeline, you flatten the two into one, right? 10 times your storage. But the problem is, what if you want to do a schema change on the small dimension table? Without the denormalization pipeline, the only thing you would need to do is to rewrite the smaller table, 100 rows, or sometimes even 100,000 rows. That's not that too many, right? But if you have a denormalization pipeline, you need to backfill the entire flattened table, which has 1 trillion rows, which is not really ideal, right? We've actually had a user that they run a metrics platform, and every time they were on Apache Druid, so they were flattening everything out. Before when they wanted to add a new metric or change a metric, it would take like days because of the data backfilling. And also this is very costly as well. It really make your schema difficult to change without significant effort. Yeah, and this is the stream processing part we just talked about, right? The state, right? Streaming join, dimension updates, multi-way joins, and backfills. Okay, so and then is what a fast join requires. So what does it need from a real-time analytical database or any analytical database to run those fast joins on the fly, to run them scalable? So first, we're gonna take a look at the life of query, right? So what actually happens inside of a database when you run a SQL query, right? So this is very abstracted, just 4 parts, right? So from SQL, and then we we simplify them, put them in the logic tree, and feed that into the planner, right? And then the planner come up with a logical plan, basically what the query is asking about, and then come up with a physical plan that's sent down to the storage layer. The storage layer scans the data, only the data that it needs, the planner think it needs, and then send it back to the query engine, to the execution engine, to either process the data in parallel or process them with one instance, right? So we're in this section, we're gonna talk about first data movement, or this is honestly actually distributed computing, and then we're gonna talk about query planning, and then we're gonna talk about execution and robustness of how do we run a SQL query fast every single time. Okay, so first is data movement. We're going to talk about data movement. So the problem under every distributed join, because like with the data amount of data we have today, right? It's basically every join has to be distributed, because a smaller table doesn't fit into the your the memory of your instance every single time, right? And the problem is, the keys are sharded. The data is sharded by some key into different nodes, right? And you would need a way to shuffle the data by your key when the query is still running, right? Then this is called data shuffling, right? You will want all of your nodes to have access to all of your data at the same time, right? So for all of the nodes to work on that one problem at the same time, right? And so does your engine support data shuffling? It's the first question. And second is it optimized for speed, or is it optimized for long running jobs that runs for hours, right? So does the intermediate results move through disk, persist to disk, or they move through memory, right? So this is the two problem you need to work at, the two questions you need to look at when you want to find a engine that is optimized for joins that can scale horizontally, and also is optimized for low latency instead of long running batch jobs, right? Let's see first is the shuffle problem. Like let's say we have a big fact table that has an impression table that has 10 billion rows of data, and then we have another fact table that has 2 billion rows of data. It's called clicks, right? So this is where really having no shuffle is going to fail 100%, right? Without shuffle, it's the left two. First is gather and it's broadcast. So gather is basically, you're basically running everything in one machine, right? Actually, still databases do that today. So on one machine, your memory needs to handle 12 billion rows of worth of data at the same time, right? And a lot of other engines that they don't support shuffle, like let's say ClickHouse open source, right? You can do a broadcast join. Basically, is you broadcasting your smaller table, right, to all of the nodes of your cluster, right? So you can basically on the fly co-locate everything, right? So for each one of the nodes, you need 3 billion rows of data worth of memory to run, right? Because it's one B that's local, that's a 10B that's shuffled by that key, right? And the 2 billion rows that are copied, the click table copied to every single node. But with shuffle, you pay in network IO, but that's scalable, right? But you have a lower bottleneck per node. So let's say you still have 10 nodes, right? Then you have one B from the impression table, and then 02B from the click table, because you can dynamically change shuffle the data to all of your nodes, right? And shuffle is extremely scalable too. Let's say you have 10 nodes here, right? What if it's 100 nodes and this memory requirement just become 120 million rows of data worth of memory? But these two are not going to change as much, because the real bottleneck is the smaller table, right? So shuffle is 100% what you need, right? And having that, how do you do shuffle is also another problem you need to ask yourself before you choose an engine, right? So first is those kind of stage through disk, right? A good example of this is I would say is the oldest map reduce kind of approach, and then the Spark, stage by stage, kind of computation that come after that, right? So basically, with every shuffle of data is shuffled to disk and persist in disk, right? So if something goes wrong, like mid time of the query, right, they can like go back and redo again from like in the middle, right? So this is really good for long running batch jobs. Not that saying they're making it slow like on purpose, but this is for the jobs that are gonna run for like a day, right? And to run them in low latency, you want the things to be pipeline driven, right? So you don't want things that are persisting to disk and all of the threads are waiting for that, right? So you would want things to move between you want the fragments, the data fragments to move between the memories of your nodes, right? To scan and then just move from one node, move to another node to memory, right? So you don't want wait time between that. So what you want is a MPP architecture, right? That's pipeline driven, right? And most of the real-time engines, real-time databases we see today has no even shuffle support. That's why you need to create vectorized views. You need to basically flatten the table, right, before you do it. And most of the warehouse and lake engines or the compute engines, the like your Sparks and all of the Spark variants, right? These are staged, right? The stage by stage kind of distributed compute, and agentic workload needs pipeline execution, right? Okay, so this is distributed compute. And then we're going to talk about planning, which is probably the most important part of running a join successfully, right? Before we even like dive into what the optimizer does and what you need, what it can do, and what happens if it doesn't do it, we need to first like ask yourself, it's with Agentic, is a good optimizer even an option now, or is a must-have, right? Before, it was like human writing SQLs, right? Let's say you're using ClickHouse. ClickHouse doesn't support join reordering, right? So your analyst or whoever writing that SQL needs to like figure out, okay, I know that this is a fact table and that's a smaller table, right? I know which one goes left, which one goes right, right? Well, I ordered the table myself, and I know, like the cardinality of each column, right? By head, in my mind, so I can write optimized SQLs. So the database don't really have to take up as big of a lift, right? Because a lot of the SQL written by human are already very, very optimized. But if you say a LM writes that query, because we collect statistic of the database to optimize the query plan, right? We know how much statistic we collect, and that's 100% not enough for the LM to handle the context window. There's no context window big enough to handle those kind of data, right? To all of the statistic, all of the cardinality, everything about a huge database that have thousands of tables, right? So do you want your LLM to optimize your query, or do you want the database to actually does a job, so the LLM can free up the context space to do something that's more important, right? So I think like today, like with this kind of new agentic workload, a cost weight optimizer is just more important even than, let's say, last year or 2 years ago, right? And this is like one of the single biggest reason why people are picking us now. A lot of that is because of the optimizer, right? And let's take a step back and talk about what cost based optimizer does, right? And there are basically two types of optimizer on the market. This first cost based is what we follow state of the art, and the other time, let's say, is rule based. Call it rule based. It's rule based. Basically, it's based on some heuristics. It doesn't really based on the shape of your data. It doesn't based on the state of your data, right? But for a cost-based optimizer, what it does, instead of guessing, it actually collects statistics from the data, like in real time. For us, I think default is every 10 minutes, right? And then it simplifies the query into a logical plan, right? And then come up with a bunch of physical execution plans, distributed physical execution plans. And then we search through the plans, we sort them by cost, and we pick the lowest one, right? And this is the state of the art for doing query optimization, right? And this is very important for joins, because In terms of join, if you order your joins wrong, if you send your runtime filters wrong, um, the a mistake that a cost-based optimizer make can be so much like worse than mine. It can be 1,000 times worse. I don't think I can mess up a job 1,000 times. Yeah. So having a cost-based optimizer without a human optimizing the query by himself is a must-have today, because if not that, you're gonna be facing many magnitudes of difference in performance. Okay, so yeah, so this is what a query optimizer can do, right? So this is actually from PhoenixAI. A lot of our capabilities, right? So from one query, like many decisions that the planner has to do, and with the cost-based optimizer, everything is based on the real-time statistic of your data, right? So then you get distributed plan, a physical distributed plan that is as well optimized that it can be. Okay, so just an example of like what a cost-based optimizer can do, right? Let's say this is runtime filter, right? So basically, let's say you have a fact table on the left, right, and you have a dimension table on the right. The fact table has many rows, and dimension table is much slower, right? What if you have a filter condition on your smaller table, but that column is not even in your fact table? What can we do? We can actually send a Bloom filter from all of the nodes that contain the smaller table to all of the nodes that contain the larger table, right? So sending out that Bloom filter itself, and so the big table doesn't have to like filter as many rows of the data, right? But sending out this Bloom filter takes cost, right? Is that worth it? This is kind of the job that the optimizer needs to do, right? So make these very small decisions to make sure that your query run really quickly. And then let's talk about query execution. We probably all know that with analytical queries, analytical databases, all of the analytical databases are columnar oriented, which means that their storage is columnar oriented, which basically means that within a file, when we store a file, right, we store them by columns instead of by rows. Why? Because let's say select something grouped by a column, we're always by analytical query by nature, we are grabbing things by column. We're computing things by column. We're scanning things by column. Everything's by column, right? By saying columnar storage, basically we're storing column. By saying vectorized execution, right? We're basically saying, okay, when we compute things in our memory, we do them in a columnar fashion as well, right? We do them in matrices, right? And also by CMD, we're saying that within the CPU cycle, right, we process multiple rows of data instead of one by one, right? So you would want vectorization, which is in memory by columnar. Your files need to be columnar, just like Parquet files, and then you want something that supports all of the modern CPU, SIMD CPU instruction sets, right? That can take advantage of the SIMD CPU instruction sets. So ideally written in a lower level language, such as C++, right? So this is a lot of the Java-based engine. We see the benchmark difference is like 10 times difference. The CMD optimization with the vectorization, that's the biggest influence factor of that, right? And also you would want something that the operator views on a shared thread pool. So each query, you're not doing code generation for each one, right? So there's no like per query overhead when it comes to thousands of QPS, which we actually see in production today. Okay, so then is robustness, right? So for a this is more nuanced, right? And the database needs to correct itself, right? To have your planned estimates, and then actually run that on the actual data, and how much the optimizer messed up, right? It needs to have its own feedback loop, right? And we're building that for our database right now. But this is something you will want, if you have requirements for not just low latency in general, but you want low latency for like 99.99% of your query, right? You actually care about like your P99 performance, right? And also the second thing is this is not that much have to do with joins anymore, but your traffic needs to be isolated, right? Physically isolated. So you will have your agentic kind of workload, and also your other, customer facing dashboards, the dashboards and reports for your executives, right? You will want resource to be isolated, so you always have, the appropriate amount of resources for all of the important workload. So one agent writes a stupid query, it's not gonna like destroy the whole thing, right? Okay, so just take a step back and review what we just went over architecture-wise, right? So query planning, you would want to have something that's cost-based, that actually collects statistics from your database and can do all of the query optimizations by itself. So you need a database that actually does database things. So it doesn't need a human or LLM to like tune the query for it, right? And data movement, distributed compute, you want data shuffling, and you want data shuffling that happens between the memory of your nodes, the pipeline execution, right? So everything is very horizontally scalable as well as fast, right? And runtime filters is just one thing. If it has it, probably has a cost-based optimizer, right? And then query execution, you want something that's written in a lower level language like C++, that can take advantage of modern SIMD CPU instruction sets, and also fully vectorized, which means that everything you process in column is also in batch, and also store things in a columnar format, store in files that are columnar oriented, right? And concurrency and stability and predictable query latency, right? You want something that has query queues and warehouse level, workload isolation, right? So actual physical isolation. Okay, so now let's introduce PhoenixAI, right? PhoenixAI is the database we've been working for the past 6-7 years that are all following this principle, these architectural design principles, right? Let's take a look at what it look like, right? From the bottom up, right? All of PhoenixAI is shared. It's in a shared object storage, right? It's with our own native tables that are in our format that can do real-time updates up to like 5-second data freshness, or bring your iceberg, right? Everything is in a shared object storage. And then on top of that, we have different data warehouses, physically isolated compute warehouses, to make sure that you have dedicated resource for each one of your workloads, such as materialized view refreshes, such as your ingestions, such as your BIs and your agent and the reports, right? You can have physically isolated warehouses, so they all have the appropriate amount of resources. And then on top of that is query planning, metadata management, connect to your external iceberg tables here, right? And then on top of that is a semantic context layer, right? So not only that we make sure that it's fast, also make sure the query is correct. I'm going to talk a little bit more about this in the next slide. Okay, so this is just a little teaser. We're going to have a dedicated webinar for this, right? So one of the bigger problem is that for agentic query, let's say for joins, right, is it's not that a lot of the metric, yeah, we have a lot of a semantic layer out there, but they all solve one problem, which is what does ARR? How do we define a certain metric, right? How do we define revenue? How do we calculate the revenue of the year, right? But it doesn't guarantee that the metric that's defined actually matches the data. That's a big problem, right? Because if you want to join two tables, right, it's also a join problem. If the granularity, if the grain of the two tables don't match, you have a fan-out problem, right? You don't want to be joining the two things, two tables on a different granularity, and you also don't want to average the average, right? That don't make sense, right? So we built a semantic context layer that with every query, it checks if the two matches, right? So always 100% we guarantee the result is correct. We're gonna have a dedicated webinar for that. Will be in the following email. And then some case studies, right? So first is Demandbase. Demandbase is account-based go-to-market platform for B2B, right? Used by thousands of businesses, right? So we have leads, in marketing, and you can go there and they estimate basically to do lead scoring, right? So the intent of the lead, right, by various of resources. So it's very complex computation, right, with many tables. Before they were using ClickHouse. ClickHouse doesn't support join at their scale, so everything needed to be denormalized. They basically 10 times their storage, and they ran 49 clusters to operate, 49 ClickHouse clusters. And then what they did afterwards, what they consolidated on Apache Iceberg, and they brought in PhoenixAI as a customer-facing analytics serving layer, right, and just say no to denormalization, run all of the joins on the fly, right? So end up they went from 49 clusters to 1, 60% less hardware, and 90% lower storage cost, right? And now they're running their same agentic workload on the customer facing analytics or serving layer that are using, that is PhoenixAI. And then it's Conductor. Conductor is an enterprise AEO platform. You have big customer include Zoom, Citi, and LV, and many more others, right? Before they were running pre-computed reports, and data would take days to reach the customers, right? And they were trying to build basically AI answer kind of agent for their customers, right? And sub-second answer was what they need, because for every question that asks, responds into many queries, right? So each one needs to be very fast. So what they did is they went into a lakehouse architecture with open table formats, and they have PhoenixAI Cloud that's running, that's querying that, serving these kind of workloads. So they have one layer for their BI, for the APIs, for the MCP agents, for their apps, for the customer facing kind of scenarios, right? And the result was, from the idea of having agentic agent that answer questions to the point that went into production, the whole thing took 2 months, because there's no like pre-processed department they needed to do. That they have their data in their lake house and just point the database to it, and that was it. Most of the time was building the application, right? And the query that typically scans hundreds of million rows. This is not a table that has 100 million rows. Scanning hundreds of million rows takes like less than 1 second, and 100% of their queries are ad hoc. There's no pre-computation. Okay, 3 things to remember, right? Agents make every query ad hoc and multi-table. And second is flattening. Denormalization is a workaround that you should not do. Even without agent, it's too expensive to do, right? And third is a fast join requires the whole architecture. Requires from query planning, from distributed compute, from scanning, how you scan the data, how you process data, everything, right? You can always go back to the slide and refer to the points I made. Okay, so that's all I have. You want to try it on your workload, start a free trial at cloud.phoenixai.ai. Oh, cloud.phoenixdata.ai, 3 days with no credit card requirement. Or you can directly talk to the team. Go to phoenixdata.ai/contact and reach out to us. If you have questions, always feel free to ask now, or on LinkedIn, or send me an email. Okay, so that's all I have. No, is there any questions? We went through the thing pretty fast. Also, a lot of slides. It's like 37. Okay, we have one question. Can I bring that to the stage? Okay, when should you still consider doing pre-join or building some kind of preset? I think that depends on like, in our opinion, it's you don't have to most of the time. Even if you do it, use something like your database own functionality, like materialized view, right? I guess it's a tough question. I guess sometimes you need like 100 millisecond. those kind of refresh, and the data don't change as much, and it doesn't update as much, the schema doesn't change as much, and you don't need like good data freshness, and you just want like really fast serving, on the things that don't really change a lot, on the scenario that don't really change a lot. I guess those scenarios do make sense, and we do have a lot of users that use our metrized views, for those kind of scenarios, so they don't run like an external, pipeline to do this kind of stuff. Okay, thank you, Henry. Any other question? Will the recording be shared with us? Yes, it will be on YouTube on Wistia. Okay, I think that's all we have for today. Oh, wait. I think there is a. Let me put it on the stage. Currently, we have some kind of preset that contains 1/10 of the fact table. Should we find it hard to do it to run on the fly? What do you mean by like 10% of the fact table? Is that just a slice of the fact table? Or that's the size of like 1/10 of the fact table? I mean, if we're doing some kind of like pre-aggregation, I guess that's fine. As long as the workload don't change as much, right? I guess 1/10, that's definitely not just a denormalization. Denormalization will make it bigger because the same granularity with more columns. Yeah, if you just do pre-aggregation, do what you have to do if the workload permits. Okay, thank you so much. Thanks so much. Thanks so much for attending, everyone. See you guys again next time. Thank you.